A little PSA before we get started. Don't skip this shit. You might look at this and say, you know what, Chili, I know what a destructor is. I can skip this stuff. But that is only a tiny part of this video. The stuff that I talk about here, every C++ programmer needs to know. Now, this video is a little longer than usual with a lot of theory and philosophy, and it also jumps around between a bunch of related topics. Don't be afraid to take a break or to come back later and review some stuff. On the wiki, I have made a detailed table of contents with timestamps for all of the topics.
Use it.
Hey everybody, I'm Chili. Welcome back to Intermediate C++ Tutorial 6. Today we're talking about destructors, we're talking about special member functions, RAII, and the rule of three. Just a whole bunch of stuff that is at the core of what C++ is all about. So stay tuned. First things first, I want to talk about some shit that I don't like. So this deal we got here, this is the meme sweeper. After we have implemented the dynamic allocation, which enables us to have, different sizes of meme fields that are selectable at runtime. So we did the dynamic allocation stuff, and that's great. The problem is when we have to free those resources, when we have to destroy a meme field, first we have to explicitly call this free resources before we delete the field. And if we forget to do that, we're going to leak memory. Now this is cancer, right? And it seems dumb because for the constructor, we don't have to do that. Constructing the object also enables us to acquire the resources. If we go to memefield.cpp, in the constructor, we call new. So those two actions, creating the object and acquiring the resources, they happen at once. They are inseparable. But for our destruction here, we have to call them separately, and because of that, if we forget to call this one first, then we get a little bit fucked, and that's shitty. So there must be a better way. Now take a look at this code here.
Look at this graph.
You guys should be able to figure out what this does just by looking at it. But we've got a class master. It embeds three objects of classes slave A, slave B, and slave C. And A, B, and C are like this. They all have their default constructors implemented, and they all output messages, constructing slave A, B, constructing master. So what do you think this is going to output to the screen? Take a second and just figure it out. When I run it, it's going to output constructing slave A, slave B, slave C, and then master, which you should have figured out for yourself, because first when we construct the object in the constructor, we construct all of the embedded objects, and then we execute the body of the constructor. So it'll be A, B, C, and then the body gets executed and it outputs this. So this much you guys should know already. Now let me introduce to you something new. Alright, now I've added an extra member function to each of these classes, and at first glance you might say, well, this looks like you just added another constructor. It has the same name, except there's one small difference. It's got a tilde at the front, and if you put a tilde and then you put the name of the class, that means you're creating a destructor, not a constructor, a destructor. And the destructor is what is called when the object is being destroyed. So you can specify some behavior anytime the object is being destroyed. And I've added this to every one of these classes here, and it's announcing its destruction. And I've also put these curly braces here around master. So it's going to construct master, then it's going to destroy master and wait. So what do you think this is going to output to the screen? Pause the video and try to figure it out for yourself. I want you to think here. Now I'm going to run the program. And here we go. Constructing slave A, slave B, slave C, constructing master, then destructing master, destructing slave C, slave B, and slave A. So you see right now it has a very beautiful symmetry here. A lot of people fuck this up when they figure, well, you're going to construct A, B, C, and then you're going to do the constructor of the body. And then when you destruct, it's going to go A, B, C, and then body. But that's not the way it goes. It goes in perfect reverse order. So A, B, C, body, body, C, B, A. That's the way it goes. In other words, when you're destroying an object, first it calls the body of the destructor, and then it calls the destructors of these objects bottom to top. And I hope you see where I'm going with this, because now that we can specify custom behaviors whenever our object dies, that is, whenever it goes out of scope for a local object, or whenever it is deleted for a heap object, we can now specify custom behavior for that, so we can fix our bullshit problem. So instead of meme field, instead of having free resources, we can create a beautiful destructor meme field. And the destructors always take 0 parameters. There's no way to pass a parameter into a destructor. And then we can implement that. So we got tilde meme field here, and then tilde meme field here, and meme field.cpp. And down here, we're going to do the same thing that we did in that ugly ass function. Let me just find it for a second here. So here's free resources. We delete, and then we set the null pointer. So I'm going to copy this, and I'm just going to paste that in here. And then there you go. Bob is your uncle. Now we don't need free resources anymore, so let's get rid of that. And let's toggle, and let's get rid of that. And if we build, we're going to get errors, and that's fine. They'll tell us where we need to go. So now we don't have to call free resources. We can just do it like this. Beautiful. You see here, after I lose, I can click and start a new one. And yeah, this keeps going. So no problems there, no crashes. And our memory is now being deleted. Now, we can go further than this, because also in game.cpp, in game we've got this allocation of memory for the meme field itself, for the object that encapsulates the array of meme field tiles. So instead of manually having a destroy field and a create, well, we can have destroy field and create field. That's fine. This can stay the way it is. But the thing I don't like about this is when we destroy the game, if it is holding a field, that field isn't going to get destroyed. It's not going to call the destructor, because there is no destructor. And of course, like I said, heap memory gets released when the program quits. So it's not too terrible, but it's still not what I like to do. So we should always have a destructor here for game. I fucking hate you. All right. Do that. And then we will go to, so in the destructor for game here, we're just going to go destroy field. There we go. And that will destroy the field if it exists. If it doesn't exist, nothing will happen. And yeah, that should just about do her. This should work fine. So it compiles, it runs, and I can do multiple run-throughs here. And when I close the program, we get no errors, nothing. Everything is working perfect. And this concept, my friends, is called RAII. Resource Acquisition is Initialization. It's a dumb acronym for a very smart idea. And the idea is that the constructor and the destructor, they're like yin and yang. They undo each other. They are the inverses of each other. So in the constructor, you're going to construct A, B, and C, the embedded objects. And once you've constructed all the embedded objects, then you call the body of the constructor. And then your object is constructed. Then you do your work. And when the object is going to be destroyed, you call the body of the destructor. And then you call C, B, and A, the destructors of C, B, and A. And then you're done. And the object is destroyed. And that's the life cycle of an object in C++. And if you write your constructors and your destructors properly, all of your memory management is going to be neatly encapsulated. It's all going to happen automatically, and you're never going to be able to fuck it up. Every time you create an object, you're automatically going to get all of the resources. And every time you destroy an object, all those resources are going to be freed. And a better word than RAII, in my opinion, is Constructor acquires, Destructor releases. That's all it is. That's all RAII means. You see this word a lot when people are talking about C++. And this is all it means. It's a very simple concept, very smart, and it is at the core of C++. So you better fucking understand it. All right, now we need to have a talk about something that is at the heart of C++ programming, and it's called special member functions. This video is ostensibly about destructors, but in many ways, this is going to be the real meat of today's video. And I never understood this stuff for the longest time, so I want to give you guys the choice that I never had.
Don't be afraid. I'm going to give you the choice I never had.
Now you might wonder what makes the special member functions special. And the thing that's special about them is that the compiler will generate these functions if they are used and if certain conditions are met. Now, there are 6 special member functions in total. 4 of them, these 4, were the original 4 special member functions, and then in C++ 11, there were 2 more added. We won't talk about those today, but the 4 originals are the default constructor, the copy constructor, the destructor, and the copy assignment. So let's start with the default constructor. We've already had a lot of experience with this guy. So as you know, the default constructor is just a constructor that takes 0 parameters. I'm going to delete our implemented one here, and you can see when we run the program, it still works. And the reason why it works is because the compiler has generated it for us. The behavior of the compiler-generated default constructor is it just calls the default constructors of all the embedded objects. Basic data member types like int, it will just leave them uninitialized, so they'll just have garbage values in the memory. Like, look here, we step over this, we've constructed master, and x is equal to negative, 8 billion or 8 million, 100 million, or whatever that number is, I don't care. So yeah, the compiler-generated default constructor just calls the default constructor for every embedded object, and, for these guys, it just leaves them uninitialized. Now, there are conditions under which the compiler will not generate a default constructor for us. If we specify any other constructor, the compiler will cease to generate the default constructor. And there you go, you get a build error. Can't find the default constructor, it's not available here. Now, we can fix that. We can tell the compiler, no, we do want you to make it for us. We can just go, master is equal to default. And this will tell the compiler, generate that shit for us, dude. Wait, that's gotta be, it's got to have the parentheses though. And there you go. Now it works fine. No problem. Now, equals default will not always work. There are situations where it's impossible for the compiler to generate the default constructor for you. So let's get a different constructor for this guy. So slave C now is not going to have a default constructor. The constructor is going to take an int. Now what happens? We're seeing an error here. Well, first of all, master is not going to be happy because it can't default construct C. So we have to specify how C is going to be constructed. So I can do that right here. I'll go C, and then I'll just put an int number in here. And now this one is happy. But we're going to have problems when we try to build. So what is the problem? Attempting to reference a deleted function. If we click here, we get this, and this error fucked up a lot of people over the beginner series because they missed inputting one thing that I had put into the code. They fucked it up, and then they couldn't figure out what was wrong because the compiler diagnostics are terrible for this kind of error. But basically, the default constructor that's generated by the compiler, its behavior is to default construct all of the embedded objects. But if one of your embedded objects doesn't have a default constructor, it can't do anything. It doesn't know what to construct it with. It can't do like this kind of thing, the compiler generated one. All it knows to do is to default construct all the embedded objects. So if one of your embedded objects does not have a default constructor, you're fucked. You can't do equals default. You have to specify it yourself, or you have to give that class a default constructor. Now, if I get rid of slave C, and if I get rid of this, you'll see that everything goes back to normal. So that's the first special member, the default constructor. And I hope you guys already knew most of this stuff that I told you. It's all been covered before already. So the next one I want to talk about is the destructor. And the destructor, I mean, I've already gone over it in this video, right? It just undoes the stuff that the constructor did. So, yeah, I don't think I need to talk about it too much here. Like I said before, every destructor, all it does is it executes the body of the destructor, and then it calls the destructors for the objects bottom to top. And the compiler generated one is no different. It just looks basically like this. It's got an empty body, and it's just going to call the destructors bottom to top for all the embedded objects. And that's it. Super simple. So let me change this constructor here just a little bit, allow us to initialize X. And what we're going to do is we're going to create master M, and we're going to pass in a 2. And then we're going to create master M2, and we'll call this master N, and we're going to pass in M. And this works. We have not created a constructor that takes a master, but the compiler will generate for us the copy constructor. And the copy constructor takes a constant reference to the same class. So it's going to take, we automatically have a constructor that takes constant reference to master. And what the copy constructor does is basically it just calls the copy constructor for every object in the class. So it's going to call the copy constructor for slave A, for slave B, and for int. And for basic types like int, the copy constructor just copies the bytes from one to the other one. So what this should do is we're going to initialize M with 2, so the x of M is going to be equal to 2. Let's just make sure that that's the case. So yeah, M, it has an x of 2, and then N is going to be copied from M, so now its x is also going to be 2. So the behavior of the copy constructor is basically just to call the copy constructors for all the embedded objects. So it's going to call the copy constructor on NA, and it's going to pass it MA. So it's going to be copied from the A of M, and same for B, and then X is going to be copied from the X of M, like that. Now, the compiler-generated copy constructor is going to look something like this in code, minus, obviously this line here. But it just calls the copy constructor for all of the embedded objects here. And so I implement this with some printing stuff, some announcement code. And in here for slave C, I do the same. I just do announcements for all the copy constructing. So if we run this, we should get an idea of what's what. Let's just run to the end and see what we get. So first things first, we've got a pubes object default constructing. So default construct slave A, B, master. And that's this first line here. Now the second line, we are going to be constructing with an int param. So constructing with the int param, if we look here, we see that it's just going to default construct A and B. There's no specifier in here for A and B. So A and B are default constructed. Then X is default constructed, or constructed with this, initialized with a value. And then we print out this message here, int param constructing master. And that's that second line done. Now the third line is going to be copying M to N. So it's going to be constructing N as a copy of M. So first of all, it's going to copy construct slave A, copy construct slave B, and it's going to copy construct int, but that doesn't announce anything. And then it's going to announce copy constructing master. And after that, it's all good. And then it's just going to destroy everything. So destroy master, slave B, slave A, master, BA, master, BA. And it's going to destroy in this order. First N, then M, then pubes. Now, the final special member that we're going to look at today is the assignment operator, the copy assignment operator. And what this one does is, well, I guess you can imagine, it copies one object to another. So if I copy n into pubes, what do you think is going to happen? Well, let's run it. So right now, n has x equal to 2, pubes has x equal to negative blah, and when we go over this, now x is equal to 2. So what the copy assignment, the compiler-generated copy assignment function does is it just copies all the members. So if you're going to do pubes is equal to n, it's going to go pubes.a is equal to n.a, and then pubes.b is equal to n.b, and then pubes.x is equal to n.x. So it just assigns all of the embedded objects to each other. Now, there are also situations where copy assignment will not be generated. So let's go into slave C. I don't believe C. Yeah, C isn't being used right now. Let's go to slave B. And we're going to create some member data. We're going to create a constant int. Let's call it x. No, we'll call it y. Whatever. Doesn't matter. So we're going to create a constant int. And this is going to create some problems for us. Build. So the first error here is an object of const qualified type must be initialized. And what that is saying basically is you can't do this shit, surely. If it's const, you gotta initialize it somehow because it can never be set after it's being created. So we can initialize it to some stupid value here in the constructor, and we have to initialize it here in the copy constructor as well. Note that the default copy constructor can handle this situation easily. It'll just initialize it with the copies value. So I could just delete our copy constructor and it would work fine. So that fixes one problem. Now we got another problem. Operator equals attempting to reference a deleted function. So why is this? Well, as you might be able to imagine, if we've got a const here, and the compiler tries to generate an assignment operator for slave B, how is it going to the default compiler generated assignment assigns all of the data members, but you can't assign to a const int. It's impossible. So it's impossible for the compiler to generate the copy assignment here. We can try to force the compiler to generate it by, doing equals default, but it's not going to work. Still going to say trying to reference a deleted function because the master assignment operator is trying to reference this one, but this one is deleted. When we say equals default, the default behavior in this situation is deleted because it cannot be generated. So if we wanted to create an assignment operator for this guy, we'd have to, implement it ourselves, and we could do assignment for any other data members, but we would have to ignore the const because it is not allowed to change. And if we do this, it must return a value. I always make that mistake. So return star this. And if we do this, it should compile fine and run. Yeah, there you go. No problem. So yeah, those are just situations when you got a const. First of all, in your constructors, you're going to have to initialize that. So you're not allowed to use the compiler-generated constructor if you got a const member. And furthermore, you're not allowed to use the compiler-generated assignment if you've got a const member because you can't assign to const. But you are allowed to use the compiler-generated copy constructor. That works fine. That will just initialize this const member with the source's version of it. And that, my friends, is the 4 original special member functions. Now, I'm throwing a lot of theory at you in this video, a lot of details. You don't have to memorize all the details right now. You don't have to memorize all the details, period. But you do have to have a general idea of what the special member functions are and, what the issues are that surround them, what makes them special, etc. Now, I'm going to show you guys a practical example of why these guys are so important. But before I do so, there's just a couple of small details that I want to tie up since we're on the topic of constructors. There's a few things that I haven't really mentioned, but that I think you'll be interested in. All right, first thing is these 2 lines here. What do you expect to be the output to the console when I run these 2 lines? Think about it, and let's see. So here we go. Fucking capture software is being a bitch. default constructing slave A, default constructing B, int param constructing master. Okay, that makes sense. That's this thing right here. We're constructing n with the parameter 69. That's going to go into x. Now, copy constructing slave A, copy constructing master. Copy constructing. We're calling the copy constructor here. Now you might think, well, this is equals, so what we're going to do is default construct doob and then assign n to doob. But that's not what happens. When you construct an object and you put an equals after it, you are actually going to be calling the copy constructor with n. So yeah, it's going to call the copy constructor, which is this one here, and this one is going to obviously call the copy constructors for A, B, and X. And B, the copy constructor, I'd made it the compiler generated one, so it doesn't announce itself. But A does still announce itself right here. So yeah, this syntax here calls the copy constructor, not the assignment operator. So that's one thing that I want you to understand. Now, the other thing I want to talk to you guys about is the concept of a converting constructor. So here, we're going to call the constructor of doob, we're going to call the constructor that takes an int. So we can initialize doob with an int, and it will call the int constructor. And we call this a converting constructor. And the same thing works for function parameters. I've got a function here, it takes a master, and I'm going to pass in an int. And what this will do is when I pass this int to this function, it is going to construct a master based on this int. So it's going to use the converting constructor to basically convert this int into a master. So if I run this program, oh shit, func must return a value. Yeah, okay. Let's make it void. Void. So if we run this program, we're doing our int param constructing, and that's for n. Then we're doing int param constructing, and that's for doob. And then we're doing int param constructing, and that's when we pass the int to func. So again, they're all calling the same constructor there. Now, sometimes you might not want this behavior. You might not want the user to be able to pass an int to func. You want them to pass an actual master object. So if you want to disable this conversion behavior, what you can do is you can go into here and you can make this explicit. And if you make it explicit, now this doesn't work and this doesn't work. If you want to create a doob that is based on an int, you've got to actually do it like this. Or you can use the curly braces and construct it like this. And the same for when you want to call func, you can't call it with an int anymore. You've got to call it with an actual master object. So you got to go, doob and pass in a doob, and then it will copy doob to here and then use that. Now, last thing that I should mention here is you might be wondering what's the difference between calling a constructor with the parentheses and calling it with the curly braces. And the difference is the curly brace is a little stricter. So let's change the parameter. Let's change it from an int to a float. So 69.0f and then 420.0f. If we try to compile this, we're going to get an error. And the error here is element 1. Give me my error. Conversion from float to int requires a narrowing conversion. So when you use the curly braces, it is stricter about what parameters you can pass in. You can't pass in any parameters where the conversion might lose data, basically a narrowing conversion. Whereas with the curly braces, it works fine. It gives you a warning, but it will compile. So if I make this an int now, you will see that it will compile and run. There'll be warnings, but it will work. I don't see them in here. Anyways, so this will give you warnings, but this one, if I try to make it an int, will just fail to compile. So that is why a lot of people prefer this version. I'm not really that consistent with it, but if you want to be super correct, this version is probably better for constructing objects. All right, now to wrap up this video, I want to show you why these special members are so important and how they relate to dynamic memory. So I've set the stage, I've introduced all the players. Now let me pose you a problem. So we're creating a class, it's called dynamic int array, and it is going to basically behave like an array, except that you can specify its size at runtime. So I can runtime specify how big I want this array, and the way I do that is I use new to allocate an array of ints, and then I can use delete in the destructor to destroy that. And I have the operator overloaded, the square brackets operator here, and it takes an index, an integer, and it returns a reference to an integer in our array on the heap. So this allows us, returning in a reference allows us to assign to it or to get from it. And then in here in main, I create a buffer, I create a dynamic int array, 5 elements, I assign a couple of values to the array, and then I print one of those values out. And if we run this, it should work. And there you go. You get 420, which was the value that we put into element 3 in the array. Press space, nothing bad happens, our memory is freed, everyone is happy. Now let's change it up a bit. Let's make a second dynamic array copying from the first one. And then let's modify one of its values. Like this. Now what do you expect to happen? Well, let's print out the values of R0 and R1 at 3. So, here's the final code. Place your bets, gentlemen. What do you think is going to happen? Well, let's run this fucker. So, R420, that's the value that we put into R0 at 3. And then after we do our bullshit, let me just see here. After we do our bullshit, R0 is now 1337 and R1 is now 1337. What fucking gives? Because remember, we only set R1 at 3 equal to 1337. We never touched R0. But somehow, R0 has also been changed. How does that bullshit even work? Well, think about what happens in this line here. We're creating R1 and we're copying R0 to construct it. So we're calling the copy constructor. Well, what does the copy constructor do? It calls the copy constructor for all of the members. Now, the only member we have in the dynamic int array is the pointer to the heap memory. And the pointer is a simple data type. So when you call the copy constructor for that, it's just going to copy the value. So now both of these arrays are going to have the same address. They're going to point to the same memory. And now when you use R1 to change some heap memory, R0, it's also going to be changed because they're accessing the same memory. They own the same piece of memory. And this is a problem for a number of reasons. First of all, it defies expectations because when you create a second dynamic array, the expectation is that they are separate and independent. Even when you do a copy initialization, the expectation is you've created a second array that just happens to have the same contents as the first one. But what we have here is a situation where these two objects are actually referring to the same memory, the same array. So you've created more like a reference than you have actually created a second array. Now, let me show you an even bigger problem we have here. Now let's change it up a little bit here. We're going to create the second dynamic array inside of these curly braces. So it's going to be created. We're going to do an operation and then we're going to destroy it. And then after that, let's see what happens. Now, because we're destroying it, we can't access it down here. It doesn't exist anymore. So let me just get rid of this code and let's run it. So we got 420, then R0, nothing gets printed out, which is weird. And if we press spacebar, breakpoint, break. And so we've hit a problem here, an exception when we tried to delete. So what is going on here? There's a lot of bullshit going on. What is it? Well, first of all, the reason why we hit that breakpoint is because we create R0, we allocate some memory on the heap, then we construct R1, and we copy the pointer. So now they're pointing to the same memory. When we destroy R1, the destructor of R1 is going to destroy this memory. Now R0 is pointing to some memory that it no longer owns because it's been destroyed. When it tries to call delete on this memory that it doesn't own, the function is going to it's going to throw an exception, and the program is going to shit the bed because you can't delete memory if you don't own it anymore. So that is why the program is basically crashing at the end there. Now, the reason why we get a blank here is basically because we're accessing memory that we no longer own. The result is undefined, so we have no idea what could be in this memory right now. And obviously, it's something that our int to string function doesn't want to process because it's not giving us any output here. So obviously this copy bullshit is no good. We can't do a copy like this where both pointers are now pointing to the same memory, because if one of them deletes it, then when the other one tries deleting it, shit is going to hit the motherfucking fan. So the question is, well, how do we do this? Well, this kind of copy is called a shallow copy. You are simply copying the value of the pointer into this one, and now they're pointing to the same region. What you want to do is you want to do a deep copy, man. You want to go in there balls deep. So what a deep copy will do is, instead of just copying the pointer value, a deep copy will allocate memory for this array here, and then it will copy all of these elements one by one over like this, and now they will both have independent memory. When you delete this one, it's not going to affect this one, and when you change something in this one, it's not going to affect it over here because they're now separate, they're independent. That's what we want to do. We want to do a deep copy with an allocation and then copying all of the elements. Now, first things first, if we're going to copy all of the elements and we're going to do an allocation when we do the copy, we need to remember how big the array was when we created it. So we'll add a thing in here, int size. We'll just set it initially equal to 0. This shouldn't matter because we're never going to call default constructor. But anyways, then we're going to go into here. We're going to go size. So there you go. This will initialize the size, make sure that we remember the size of our goddamn array. Now, for the copy constructor, dynamic int array, and it's going to be const dynamic int array ampersand source. And what are we going to do in here? Well, what we're going to do is we are going to do size is source.size. And p array is is new int source.size. So this will allocate new memory for our copied int array. Now what we've got to do is we've got to copy over all of the values from the source to the current one being constructed. So we'll go for int I is equal to fucking bullshit 0 as long as I is less than size I plus. And then for every one of these we're going to go p array at I is equal to source.parray at I. Or we could have just done, source at I. That would have been fine as well. So this will copy them all. What is your goddamn problem? Operand types are const. All right, because this one isn't const. So if we want to make a const version of that, whatever. Let me just show you this again. We've done this before, but operator square brackets int index, and we make it a const version, and we return this like that, and now this guy is happy because remember this was a const, so we can't call a non-const function on it, so we need a const version of that. Fine, whatever. So this will do the deep copy. It will allocate memory for the new array, and then it will copy the elements over. Now if we do some bullshit in here, it should work fine. So let's first run this and see how she goes. 420, and after we do our bullshit 420, and it doesn't crash. So there you go. This assignment didn't affect the original, and this destruction didn't fuck over the original. Everything is now motherfucking sweet. Now let's look at another situation, the copy assignment. What is going to happen when we do copy assignment from 0 to 1 and then try to modify something in 1? Well, again, we're going to get our empty output and we're going to get our breakpoint because of an exception. So, no good. Why is it no good? Well, I'm sure you can figure that out. The default, the compiler constructed copy assignment, what it does is it is going to just copy all of the data members. So it's going to copy size and it's going to copy p array. It's going to copy the pointer value. And now, again, you're going to get the bullshit situation where they're both pointing to the same memory. In fact, not only are you going to get the bullshit where they're both pointing to the same memory, you're also going to lose the pointer to this memory. So this memory is now leaked. Now they're both pointing here. Then when this one destroys this one is going to be accessing memory that no longer exists. So it's just really bad. It's a really bad situation. So what's the solution? Well, obviously, you're going to have to implement the copy assignment yourself as well. So the prototype for that is going to look like something like this. Now, you're going to have to do some extra stuff for the assignment because the int array is probably going to be already owning some memory. And what you want to do is you basically want to create new memory that's the same size as this one. You want to destroy this memory and then you want to copy from here to here. The reason why we're creating new memory is because you might be copying from an array that is a different size. But you could also make a check in there to see if it's the same size, but we'll just forget that. And we'll just destroy the current memory and create new memory and then do a deep copy. So the way you do that is you go, well, first of all, you go delete p array. And I like to do this even though it's not really important here. Set it to null pointer after you delete it. Just good practice. So now we've freed up the array that we currently own. Now let's create a new array that is the same size as the source. So we go p array is equal to new int source.size. And now we got to do size is equal to source.size. There we go. So now we've set up the memory, and all we got to do is copy. So all we got to do for that is just copy paste this guy and put her in here, and that's it. That should do her. And now if I run this bullshit, it should work. No, because I got errors. All right, must return a value. The same error that I always make.
Gee, Ray, what do you want to do tonight?
The same thing we do every night, Pinky. Try to take over the world.
Return. Star this. All right, now let's go. And here we go. 420, 420. No problems, no errors. It just works now. And that's it. So when you are allocating memory like this, when you're managing dynamic memory with a pointer directly, and you're allocating it and you're freeing it in a destructor, you must always do something about the copy constructor and about the copy assignment, because the default shallow copy is almost never what you want. It is almost always a bad deal. So you got to implement this to yourself. Now, this leads us to a very important concept in C++. It's called the rule of 3. And the rule of 3 states that if you implement any one of these 3 functions, the copy constructor, the copy assignment, or the destructor, you should be implementing all of them. Because if you're implementing one of them, that means you're doing something that the default of the compiler is probably not compatible. So if you implement any one of these guys, implement them all. That's the rule of 3. Learn it, love it, live it, because this shit is, if you don't learn this shit, you're gonna fuck yourself over again and again. Now, this is the rule of 3. There's also another one called the rule of 0. So what is that? We'll take a look at our database class and our entry class too. These classes, they don't have any dynamically allocated memory that we're managing ourselves. There's no pointers, there's no new and delete, right? So we don't have to implement the destructor, and we don't have to implement the copy constructor or the copy assignment. The defaults all do exactly the thing that we want them to do. They just work. Like in add here, I'm using the assignment here, and it just fucking works. I don't have to think about it. So the rule of zero says that if you aren't doing anything that needs you to mess around with the destructor or the copy assignment, copy constructor, then don't implement any of them. Stick with the compiler defaults. Don't implement them unless you have a good reason. That's the rule of zero. So yeah, the rule of three, the rule of zero. Now, there's a couple things that we can do here. For example, you might notice that the stuff we're doing in the copy constructor is pretty much the same as the stuff we're doing in the copy assignment. The only difference is we're doing this delete at the beginning. But what we can do is we can just take our copy constructor here, and we can make it call our copy assignment. So we can go star this is equal to source. And what that's going to do is, well, first of all, it's going to try to delete. But because when we enter the copy constructor, the first thing that's going to happen is it's going to default construct all of the members. And since they have initializers, that means it's going to initialize them to 0 and null pointer. So when you do this, trying to delete a null pointer has 0 effect. So these lines won't do anything. And then you're just going to do your standard initialize, allocate memory, and copy. So you can save a little extra code duplication and call your copy assignment inside of your copy constructor, and that'll work fine, in most cases at least. Now, the other thing you can do is, let's say you're not using assignment at all. You're not going to use copy assignment. Instead of implementing it, just fucking delete it. Just say, fuck, I don't need this shit. I'm just going to delete it. And then anytime you try to use it, the compiler's going to say, don't do that. It's dumb. And that means here, and I guess that means here. Okay, well, I kind of fucked myself over because I was using that, but you get the idea. The idea is, if you don't fucking need one of these functions, just fucking delete it. Just say no. Just say no to drugs. Delete. First learn how to type, and then say no to drugs. So I can get rid of this now. Say, well, I'm not allowed to do this, so fuck everything in the whole world. And there you go. So that's another option, just deleting shit if you don't need it. And that's it for today. We learned a lot of important C++ theory in this video. We learned about destructors, we learned about RAII, we learned about special member functions, rule of 3, rule of 0, deep copies, all that good shit. Now, I don't expect 100% retention of all this stuff. It's a lot of rules, and it's a lot of theory / philosophy, but as long as you're aware of the issues, you'll be able to handle the problems of this stuff when they come up. You'll know where to start, at least. The true way to fully learn this shit and internalize it is to deal with it organically. And I'm not talking about whole foods here. I'm talking about practicing it, wrestling with it as you code up your own projects. That is how you're going to basically build it inside of you. The knowledge. Now, for the homework, I've got something a little interesting this time. I'm not going to go into super detail about the homework here, so make sure you check the wiki for the detailed instructions. But basically, what you're going to be doing is you're going to be implementing a container like the dynamic int array that we implemented in the tutorial, only it's going to be a little more complex, a little more involved. It's going to be a simple stack, not an array, and it is going to be implemented as a linked list internally. Now, I've already talked briefly about stacks and linked lists in previous videos, and I'm going to put the links to those videos on the wiki, but you're probably going to need to do your own research in order to be able to implement this stuff in code. Now, the interesting part about this homework is I've implemented a battery of tests that will be executed using the container that you create. So there's a whole bunch of tests here, and what you've got to do is you've got to implement this stack container. You've got to implement these functions so that they pass all the tests. And not only does it have tests, but at the end it will also detect any memory leaks, so you can check to see whether you've properly handled all of the memory freeing and allocation. You can look at the test code if you like, but it won't be necessary in order to complete the homework. You'll also have access to all the string functions that we've created up until this point in chilistring.h in the namespace chili. But again, it won't be absolutely necessary to use these in order to complete the homework. On the other hand, you might want to try developing the stack class in a separate project, adding a bunch of your own tests and output the console code. And then when you get it working, transplant it into this project, this solution here, and run the tests on it. The detailed rules are going to be written in the wiki page, but in general, you're not allowed to modify any of the test code, and you're not allowed to use stuff from the standard library. This is actually the last homework that I'm going to be placing that restriction on you, by the way. So good luck. That's it for this video. If you liked it, please click the like button. It helps a lot. And I will see you soon with some more C++.